Let us quickly recap the velocity time graph before we derive the SUVAT equations. Here we have a graph showing the motion of a body. So the body starts from this point here, which is 20 meters per second. So this is the initial velocity. So we're going to describe each section of the graph. So let us label this part of the graph as A, this part as B, and this part as C. So we're going to describe the motion of the body at point A here. The body is accelerating here. So we can write constant acceleration. Now it's important to understand this section here because the acceleration is the gradient of this line. So we can write acceleration is a gradient. Is equal to the gradient. And the gradient there is the change in the y value there. So if we just make a little sketch here on the right angle triangle, so the change in this value here would be 20 from 40, and that's 20 meters per second, and the time here is 3 seconds. So the acceleration there then would be 20 divided by 3, and that would be 20 meter per second square. 20 over 3 meter per second square. That would be the acceleration. Okay, let's look at part B of the graph. Now the body here would be under constant velocity. So it's not changing, it's fixed at 40 meters per second and it's just traveling there like that. So that's constant velocity. That's 40 meters per second. And section C here, the body is under constant acceleration, or we say it's decelerating. So you can write constant and we put in bracket here deceleration. And here the value would be negative. So let's look and see the height here is 40 meters per second, and the time here is 6 from 8, and that's 2. So here minus 40 divided by 2, and that's going to give us minus 20 meter per second square. Now the next part of the graph that we need to look at is the area underneath this section here, the displacement. And that is in meters because that's the distance covered. Now it's the area, so we can write here the displacement is the area. The area is equal to the displacement. And that is in meter. So the area underneath here would be the displacement or distance covered by the body. So what we're going to do is to find the area of this and then determine the distance. So we're going to divide this up into 3 sections. So here we have a trapezium, and we have a rectangle and a triangle. So we're going to find the area of these and then we add them up, and that would be the total distance covered. So for the trapezium here, we have this side as 40 meters and the other side here is 20. So these are the parallel sides, and then the height there would be 3. So the area of the trapezium is the sum of the parallel sides, which is A plus B divided by 2 times it by the height. So in this case, we're going to have 40 plus 20. 40 plus 20 divided by 2 times it by the height there, which is 3. So 40 and 20 is 60 divided by 2, that's 30 times 3, that's 90. So that would be 90 meters for this section. So for the rectangle, it's just going to be the length times the width. That would be the length times the width. So here the length is 40. And this measurement from here to here is 3. So 3 times 40, that's 120 meters. And then the area of the triangle here is the base times height divided by 2. So here the base is 2 times the height here, which is 40. So it's going to be 2 times 40 divided by 2. So that gives us 40 meters. So 120 plus 40, that's 160 plus 90, that's 250 meters. So the displacement here, or distance, is 250 meters. Okay, so we have 90 plus 120 plus 40. So it's 250 meters. So that would be the distance covered. It is really important to distinguish between displacement and distance. So this is our starting point here, A. This point here is our starting point, and we travel all the way going in this direction, and then we come back to this point here. This is our finish line. Going in this direction here, we travel 100 meters. And coming back to this finish line here, we travel 60 meters. So here, the distance would be 160 meters. So let's write that down. So the distance is 160 meters. So the distance here is a scalar quantity. Now the displacement is measured from the starting point, and it's a vector in a specific direction. So here at this point, the displacement would stop at this point here, and the direction here would be east. So it would be 40 meters east of the starting point. So the displacement there would be 40 meters. 60 from 100 would be 40 meters. So displacement is a vector, and that would be 40 meters east of the starting point. So we can put east here. So the displacement has direction, and it's a vector. The SUVAT equations are essential tools in physics and mathematics, and so in this video I'm going to derive these equations, and after which I will work through a range of questions. So SUVAT, what does it mean? So let's write it out here. Okay, so the S here denotes the displacement or distance. And that is in meters. The U here indicates the initial velocity. And that unit there is meter per second. And the V here indicates the final velocity. And that's meter per second as well. And the A here is the acceleration. This acceleration is constant. And the T here represents time. And that is in seconds. The acceleration here is meter per second square. That's the unit there for it. Okay, so let us look at this scenario. Let's say I'm driving my car and at point A, at this lamppost, at point A here, I'm traveling 30 meters per second. And at lamppost B, I'm now going at 50 meters per second. So the distance between point A and point B is what we want to find, and also did I accelerate. So let's write here then A, we want to know the acceleration and also the distance, which is the displacement S. Now we could illustrate this on a velocity time graph, so let us make a sketch to have a clear understanding of this. So along the vertical here, this will be the velocity. The unit is meter per second. And on the horizontal here, that's the time, and the time is in second. So to illustrate this on the graph, my initial velocity at A would be at this point, so this is 0 here. So at A here, I'm going 30 meters per second. This is my initial velocity, and that would be U. And my point at the final velocity there at 50 would be V. So I'm going to denote that as V. And to sketch this graph then, it says that I travel between U and V in 5 seconds. So here, the time to get to V is 5 seconds. So that's the sketch of my graph. So here we want to know whether we had accelerated, and also we want to know the distance. So let us first focus on the acceleration. Now by looking at the graph here, the acceleration is a gradient of this line here. So acceleration is equal to the gradient. How do we determine the gradient from this? Well, the gradient is a change in the y value over the x value. So if we annotate this diagram here, the change in y here would be v minus u. That would be v minus u. And the change in x here is just t. So since the acceleration is a gradient, it means that the gradient here would be the change in y, which is v minus u divided by t. So let's write v minus u over t equals to the acceleration. So we can work out the acceleration here because we have the final velocity, which is 50, minus u, which is 30, divided by the time, which is 5 seconds. And that would equal to the acceleration. So here, 30 from 50, that's 20, and 5 into 20 goes 4. So the acceleration here then is 4 meter per second square. Okay? So that's the first thing we have seen there, that it's really accelerated. Now we're going to derive the formula. If we multiply both sides by t here, what we have is v minus u is equal to at. And if we add u both sides, then we have v is equal to u plus at. That's equal to u plus at. And this is the first SUVAT equation. And from this equation, we can derive all the other equations. So this is equation number 1. Okay, so now that we have derived our first SUVAT equation, we're going to look at the distance covered underneath this graph. So let's annotate this graph. So the distance covered is the area underneath this velocity time graph. So here we have this section here as the area, so we can write area here. And the area underneath here we said is the displacement or distance. Now this is a trapezium, as you see here, so the parallel sides here would be v, so we can annotate this as v, and this is u, and the height there would be t. So the displacement s, so we can write, let's write area is equal to the displacement or distance. Okay, so how do we find the area of this? Well, the area of the trapezium is the sum of the parallel sides, so it's going to be s, which is the displacement, and the sum of the parallel side here would be v plus u divided by 2 times it by the height, and the height here would be t. So this is our second SUVAT equation. Okay, now from equation number 1 here, we know that v is equal to u plus at. So from this equation 2, if I replace this v with u plus at, we could derive the third SUVAT equation. So we have s is equal to v plus u over 2 times t, and here I'm going to replace this v by u plus at. So here I'm going to have u plus at plus u, all of this over 2 times t. So u plus u here would be 2u divided by 2. That will be just u, and we multiply by t, so that we get is ut. So s equals to ut plus, now we have at times t, so we get at squared, and we divide by 2, so it's just a half, divide by 2 there, that's a half at squared. So this is our third SUVAT equation, and we can derive our fourth SUVAT equation, because equal to v minus u, all of that over t. We found out that earlier on. So if we rearrange this formula to make t the subject of the formula, so t would equal to v minus u, all of that over a. This t, I'm going to replace it with v minus u in our second equation. Then we can get our fourth SUVAT equation. So s here is equal to v plus u over 2, v plus u over 2 times t, but t here is v minus u, so I'm going to replace t with v minus u. So this then would be v minus u all of that over A. And if we expand this and simplify, here we have v squared minus u squared, all of that over 2a. And if we multiply both sides by 2a, what we have is 2as equals to v squared minus u squared. And if we add u squared both sides, then we get v squared is equal to u squared plus 2as. And that's our fourth SUVAT equation. So we can write v squared equals to u squared plus 2as. And that's our fourth SUVAT equation. So what we're going to do now, we're going to work out the distance covered. Okay, so from this formula we could find the distance covered, or even this formula as well. So we have S is equal to u plus v over 2 times t. So let's work this out and see what we get. So we have S then is equal to v plus u, and v here is 50 plus u, which is 30, all of that over 2 times t, which is 5 seconds, times 5. So 50 plus 30, that's 80, divided by 2, that's 40. So 5 times 40, that's 200 meters. So the distance covered is 200 meters. So this is 200 meters here between A and B. And the acceleration we got was 4 meter per second square. So yes, I have accelerated, and the distance that I traveled then is 200 meters. You could use this formula and you would get the same value. So if we put in here S is equal to the initial velocity, which is 30, times 5, which is t, plus a half times the acceleration, which is 4, times t squared, which is 5 squared, times 5 squared. 5 times 30, that's 150. Half of 4 years, 2. So 2 times 25, that's 50. And you would get 200 meters still. And we could work out the v here, the final velocity, and we would still get 50. So if we input here v, we have v squared then is equal to u squared, which is 30 squared, plus 2 times the acceleration, which is 4, times s, which is the distance, 200, so that's 900. So 2 times 4, that's 8 times 2, that's 1600. So what we get there is v squared is equal to 2500. Take the square root. What we get is we get the final velocity, which is 50 meters per second. So this is a vertical motion question. Now, so we have part A, you want to find the maximum height reach. So part A, we want the height, maximum height reach. So let's write out SUVAT. What we're going to do is to identify what is given. So here the initial velocity is given, which is u. So that's 40 meters per second. Final velocity would be 0. and the acceleration due to gravity there is acting toward the center of the earth. It's going to be minus 9.8 meters per second squared. Now, so we only need 3 variables to work out the question asks, which is s. So t here is not required in part A. Therefore, we can use the formula v squared equals u squared plus 2as, since we have u, v, and a. So u here would be 14 squared plus 2 times minus 9.8 times s, and v here would be 0 squared. So it means that 14 squared here is 196. We subtract 14 squared both sides, so that's minus 196 here. And that is equal to 2 times minus 9.8, that's minus 19.6 times s. So we divide both sides by minus 19.6. So s here is equal to 10 meters. So the distance, the maximum height reached is 10 meters. Part B. We want to find the time. So we write out SUVAT. So we want to find the time. So we are given the initial velocity, which is u. We are given final velocity, which would be 0, and the acceleration is acting toward the center of the earth, so it's going to be minus 9.8. We want to find time, so s here is not important, so we have 3 variables, so we can use v equals u plus at. So it means that v is 0, u is 14, a is minus 9.8 times t. So we subtract 14 both sides, so what we get is minus 9.8 times t is equal to minus 14. So we divide both sides by minus 9.8. So that's minus 14 over minus 9.8. And let's see what we get for that. So by inputting this in our calculator, we get t as 1.43 to 2 decimal places. T is 1.43 to 2 decimal places. Now, the time of flight here would be a half, but we want for the whole journey, so we need to double this time. So what we get there is the whole journey time for the whole journey would be 2 times 1.43. So that would be the time for the whole journey. So it's 2.86 seconds. That's in seconds. Okay. In this question, divers are diving from a rock which is 36 meters above sea level, and you are asked to calculate how long the dive lasts and also the speed with which the divers hit the water. So the first part of the question, we need to work out the time. So let's write SUVAT. So we have S Okay, so S is given, which is 36 meters. The initial velocity is 0. The acceleration is acting toward the center of the Earth, therefore it's minus 9.8 meters per second squared. And you're required to find the time. So there are three variables given here in the question. This is not important. That's not what is required. So we want to find the time in this part of the question. Therefore, we can use S equals ut plus 1/2 at squared. S is 36 meters, but since it's above sea level, therefore it should be minus 36. Then we're going to have u, which is 0, times t, so that's just 0. So what we have is a half a, which is minus 9.8 t squared. Multiply both sides by 2, so that's going to be minus 72, and that is equal to minus 9.8 t squared. We divide both sides by minus 9.8, therefore t squared is equal to 72 over 9.8. So to get t, we take the square root both sides, therefore t equals to the root of 72 over 9.8. Let us input this in our calculator and see what we get for the answer there. So what we get is 2.7 seconds to 1 decimal place. So 2.7 seconds, 1 decimal place. So that's how long the dive lasts. Now we want to find the speed. That's the second part of the question. So we have SUVAT S U. Okay, so we want the speed, which is the final velocity. We have acceleration, which is minus 9.8 meter per second square, and we have the time, which is 2.7 seconds. We have the initial velocity, which is 0. So S is not important in this case. So we want to find V. So we know that V is equal to U plus AT. So U here will be 0 plus A, which is so we have V is equal to U, which is 0 plus A, which is minus 9.8 times the time, which is 2.7. So what we get there is 26.5 meter per second. So the velocity is 26.5 meter per second. So in this question, the ball is projected vertically upwards 20 meters per second from a point H above the ground. The ball hits the ground 5 seconds later, and we want to find the value of H, which is the height, and B, we want to find the speed at which it hits the ground. So part A, let's write out SUVAT. So we are given the initial velocity, which is 20 meters per second. Acceleration there is acting downwards, so that's going to be minus 9.8 meters per second squared. And we want to find the value of, we have the time, which is 5 seconds, and we want to find H, which is S, which is the distance. So the final velocity here is not important in part A. So let's work out that and see what we get. So we have S then is equal to ut plus a half at squared. So we want to find S, then we have the initial velocity, which is 20, and we have the time, which is 5, plus a half, minus 9.8, and we have time, which is 5 squared. So what we get there is, that's 100. Right, so we have half of minus 9.8, that's minus 4.6 times 25, that's minus 122.5. So what we get there for S is minus 22.5, indicating that the height is above sea level, therefore S is equal to 22.5 meters. And that's the height H. Part B, you want to calculate the speed at which it hits the ground, so let's write SUVAT. We have the initial velocity, which is 20 meters per second. We have acceleration, which is acting toward the center of the earth, so it's going to be minus 9.8. And we have the time, which is 5 seconds. So we want the speed. So S is not important in this case, so we have then V equals U plus AT. So V then is 20 plus the acceleration, which is minus 9.8 times 5. Let's input this in our calculator and see what we get. So here we get minus 29, indicating that the velocity is acting downwards as well. So it means that the velocity is 29 meters per second. V equals 29 meter per second. So minus 29 there is indicating the direction of the ball when it hits the ground. A steel ball is released from rest above a cylinder of liquid as shown in figure 3 here. The ball descends vertically in the air, then in the liquid until it reaches the bottom of the cylinder. So here we have the ball, and it is released until it touches the surface of the liquid. The vertical distance from the bottom of the ball to the surface of the liquid is 0.16. That's the height. We are asked to calculate the time taken by the ball to fall to the liquid surface from where the point is released, giving your answer to the appropriate significant figures. So part A then, we just write SUVAT. So we have S as 0.16. The initial velocity is 0. The ball is acting downwards toward the center of the earth. So it's going to be minus 9.8 meters per second squared. We want to find the time t. So the final velocity is not important. So we have three variables. We have S, U, and A. So we can use the formula S equals ut plus a half at squared. Since the ball is above the surface of the liquid and is falling downwards, it's going to be minus 0.16. U here is 0 times t, that's just 0, plus a half A is minus 9.8 t squared. We multiply both sides by 2, so what we get there is 0.32 minus 0.32, and that is equal to minus 9.8 times t squared. Divide both sides by negative 9.8, so t squared then is equal to 0.32 over 9.8. So t equals to the square root of 0.32 all of that over 9.8. So let's get our calculator to work this out. Square root of 0.32 all of that over 9.8. So what we get there is to three significant figures, that's 0.181. So the time is 0.181 seconds to three significant figures. So that's part A. So the time then t. So let's write then. The answer is 0.181 seconds. Now calculate the velocity. So we have then that's part A, part 2. So we're going to write then SUVAT. So we want to find the velocity when the ball reaches the liquid. So the initial velocity is 0, and we have the acceleration, which is minus 9.8. We have the time, which is 0.181. So we want to find the final velocity. So S is not important in this case, so we have three variables, U, A, and T. Therefore we can use V equals U plus AT. The initial velocity is 0, so we have the acceleration, which is minus 9.8 times time, which is 0.181, and we input this in our calculator. So we have 0.181 multiplied by minus 9.8. So that's minus 1.77. So the velocity then is 1.77 meter per second. And the minus there indicating that the velocity is acting downwards.